Okay, so welcome everybody. So today we have great pleasure to host Roee Ozeri from the Weizmann Institute in Israel. So he will talk about quantum logic detection of ultra-cold atom-ion collisions and reactions. So just maybe to mention a few facts. So Roee, I think, studied his undergrad and PhD at Weizmann Institute, then spent postdoc at NIST in Boulder, working in the group of Nobel laureate David Wineland. And then I directly after this started as a faculty member at Weizmann, where now he is, I think, full professor and vice president of Weizmann. So we are also very happy that you found time to give a seminar. And the screen is yours.
Thank you very much, Michal, for the kind introduction, and thanks all for having me. I guess a year and a half ago, I would gladly come to Warsaw and visit your institute and give the seminar in, face to face. But I guess also the fact that we're doing this in Zoom allows for more availability. So, anyways, thanks for having me. What I'd like to tell you about today is about several experiments we performed in the last few years using ultra-cold atom-ion mixtures. What you see here, the red dot, not the laser pointer, but the red dot in the picture is a single trapped ion. In our case, it's strontium plus that is immersed in a cloud of, anywhere between 10 to the 4 and 10 to the 5 ultra-cold rubidium atoms. Both of these at least begin at a temperature of a few microkelvin. I chose as a title the last topic I'm going to get to in my talk, which is how we use quantum logic techniques, and I'll explain what I mean by that, to study atom-ion collisions and reactions and chemical reactions. Before I move into the physics, I want to say that this is an experiment we've been working on, I guess, 12 years already by now. And, it was actually, I'm talking about it, but the people who actually worked on this experiment are 8 graduate students and postdocs who have been working very hard and, putting all their effort and talent into this. And I'd like to recognize them before we begin. So I think, if you're from the AMO community, you're probably very familiar both with trapped ions technology and neutral atom technology. Trapped ions or laser-cooled trapped ions have been around since the end of the 1970s. Here you see an example, again, from our lab of 8 trapped ions. They're laser-cooled to low temperatures. Their Coulomb repulsion forces them to arrange in a Wigner crystal. They're probably the most precisely controlled quantum systems that we have today, and that's why they serve as a platform, as a test bed, both for quantum computing, as very precise optical atomic clocks for precision measurements and so on. Neutral atoms have followed with laser cooling techniques a few years afterwards. These systems, whereas in trapped ions, the interaction is pretty trivial. The Coulomb repulsion does not allow for any wave function overlap. Here, the wave functions of ultra-cold atoms overlap. That's why their spin statistics matters. They show BC or Fermi degenerate behavior at very low temperatures. Ultra-cold interactions are really at the basis of ultra-cold atom physics. And people have seen superfluidity, both in Bose and Fermi gases. Strongly interacting dipolar gases have been studied. Superfluid Mott insulator has been under experiment. So really, the statistical mechanics and the many-body interacting nature of these systems is under heavy study for the past 20, 30 years. Since 2009, people have started experiments in which, and I think it was started by the group of Michael Kohl back then at Cambridge, and then Johannes Denschlag at Ulm. People have studied mixtures of ultra-cold atom and ions. This is a new playground, and it differs from the 2 previous playgrounds in many ways. Ultra-cold atom-ion chemistry is different, and it's important because it dominates interstellar molecular formation. You can think of the ion as a highly localized probe of these ultra-cold gases, and along these lines, people have come up with theoretical ideas of how to use these systems in order to emulate condensed matter systems, for example, the behavior of spin defects in metals. So there's a lot of motivation into studying these systems, and that's why following these initial experiments and these theoretical ideas, I think today, and I apologize if I forgot any of the labs that are in the game, I think today we have probably 15 or maybe up to 20 experiments in the world that are studying these mixtures. And as you can see by the choice of neutral atoms and ions, this is a fairly democratic community, and I think we see more and more pair choices coming into the game. In our lab at the Weizmann Institute, we use strontium plus ions and rubidium atoms. As you'll see shortly, one of the special things about these is that the mass is almost exactly identical. Of course, it depends on the isotope you choose, but up to 1 or 2%, the mass of rubidium and strontium plus is exactly the same, and that has implications in the type of physics that we study. People have been thinking about even classical interaction between trapped ions and neutral atoms. Probably the first to look into this problem, examining the behavior of current that was flowing through gas tubes 100 years ago or so, was Paul Langevin. And Langevin classically have shown that similar to many other cases in the minus one over r to the fourth potential that is governing the interaction between trapped ions and neutral atoms, or ions, charges, and neutral atoms. If the collision happens above a certain critical parameter, then all that happens is there's a very small deflection of the trajectory in the center of mass frame. These are glancing collisions, and they're not very efficient in transferring momentum. However, if one goes below that critical impact parameter, BC, below that critical impact parameter, and you can think of that impact parameter as defining the cross-section for collision classically, then what you get is this inward spiraling trajectory that eventually leads to close contact interaction. Chemistry would therefore be dominated by the Langevin collision rate. The peculiar thing about the Langevin rate is that the Langevin rate is independent of the collision energy. And this is because the Langevin cross-section, if you like, the impact parameter square, scales as 1 over the square root of energy, or 1 over the velocity. And because the rate is proportional to the cross-section times the velocity, in the case of Langevin rate, you get a Langevin rate which is energy independent. That means that chemistry is going to be energy independent in the classical regime, and also momentum transfer. These glancing collisions are not very efficient in transferring momentum. Momentum transfer is going to be energy independent. How do we connect that classical regime to the semi-classical regime? So quantum mechanically, we can write the cross-section semi-classically. We can write the cross-section as a k-dependent prefactor times a sum of contributions from different partial waves. And here we would sum from L equals 0 partial wave all the way to the maximum partial wave that is allowed given our collision energy, and then a factor that goes like 2L plus 1, and then a sine squared of the phase that is acquired while colliding on this partial wave. If we have many partial waves, it's a semi-classical regime, then the sine square term averages to 1/2, and we actually recover the Langevin rate actually up to a factor of 2. So this is a way to connect the classical and the semi-classical regime. Again, within the semi-classical regime, the cross-section goes like 1 over the square root of energy, and the rate is energy independent. We can of course dive into the quantum regime. Quantum regime would be that of having very few partial waves. The challenge with these polarization potentials is that they're relatively soft, and that means that the centrifugal barrier is relatively far away. The centrifugal barrier of the P wave, the L=1 partial wave, is relatively far away from the origin. In our case of strontium plus rubidium, it's almost a quarter of a micron away from the origin. That means that in order to get to the S-wave regime, we need the de Broglie wavelength to be large as compared with that distance. And that means that the energy is below the height of the centrifugal barrier, which in our case is at 18 nanokelvin. So very unlike the situation of neutral atoms, where people go into the S-wave regime at a millikelvin temperature, for us, in order to go into the S-wave regime, we need to be with a de Broglie wavelength that is 2 orders of magnitude larger, and an energy that is about 4 orders of magnitude colder, and that is a serious challenge. And as you see, it's not easy. It's not easy to get there. So how would we see signatures of quantum scattering over these potentials? So one example of a quantum signature for these collisions would be a case where, as we approach the quantum regime, we arrive at the collision energy that is on resonance with a quasi-bound state that is held by one of the centrifugal barriers. It can be the P wave and other higher partial waves. If that happens, then we can think of this situation as very similar to a matter wave Fabry-Perot cavity situation. In this case, the amplitude of the collision would build up within this bound state, and the cross-section for collision would shoot up. And people have calculated that if you calculate the cross-section, and again, we don't know the details of this interaction potential sufficiently well to know where these resonances would be exactly, but we can choose some potential parameters and get an example for a possible spectrum in this collision. Again, for rubidium strontium plus, you see that even up to 20 partial waves, we expect to see shape resonances at energies which even go all the way up to about 10 millikelvin. These are relatively narrow resonances of a width of about a few tens of microkelvin. So this would be an example for a deviation from the Langevin semi-classical regime and a clear signature of quantum scattering. And I think that any really significant deviation of the dependence of the cross-section from the 1 over square root E that the semi-classical Langevin regime predict would be a clear signature of quantum scattering. And actually, I should say maybe already at this point, the 2 recent experiments, actually in both Michal has been heavily involved and a partner, one by the group of René Geritzma in Amsterdam, and one by the group of Tobias Schatz in Freiburg, has recently seen very clear signatures of quantum scatterings in these ultra cold mixtures. Now, of course, when we look at the interaction potential between atoms and ions, we see something that is much more rich and complicated than that single polarization potential curve that I've shown before. Of course, for every internal state of the atom or the ion at very large separation, we would get a different molecular potential. And again, here you see an example for rubidium strontium plus. One actually peculiar trait of working in most of these systems is that the entrance channel to the collision, where an earth alkaline ion would be in the ground state and an alkaline atom would be in the ground state, would not be the molecular ground state. Actually, the molecular ground state would adiabatically follow to a situation where the alkaline atom is ionized and you get a noble gas ion, and the earth alkaline is neutral and has a pair of electrons in the ground state. This is a significantly lower energy. Again, for the case of rubidium plus strontium, there's an energy that is equal to the energy of a IR photon, which means that as we go through the collision, there is a chance for us to radiatively go down to that ground state. This is a radiation, because these are off resonance, a photon has to be emitted in order to go here. It can actually only connect the singlet molecular potential here to the singlet ground state of neutral strontium and rubidium plus. And what I'm showing you here in this little movie, let's see if it actually plays. Maybe I need to get rid of my, maybe I need to get rid of my laser pointer to get there. No pointer. I can't get rid of my pointer for some reason. Too bad, because it's a good movie.
There was a pointer for a short while.
No, there is a pointer, but I don't want a pointer. I want to run the movie. So I need let's see. Yeah. Well, anyways, I'll skip the movie. What you would have seen here is, you know, all these bright ions certainly turn dark, and the reason they turn dark is because they change into rubidium plus slowly by charge exchange collisions. And in our case, it happens every 10 to the 4th Langevin collisions or so. So it's a pretty rare, it's an off-resonant radiative event with a fairly small Frank-Condon factor, and that's why it's not a true impediment to our experiments, but it's an inelastic process that can definitely occur. The machine that we have in our lab is the following. We have 2 vacuum chambers. In the lower, we trap strontium plus atoms. In the upper, we collect rubidium atoms. We load them into a laser trap. We then load this laser trap into a one-dimensional optical lattice that you see here. It's this one-dimensional array of pancakes of light, you know, bright, dark, bright, dark. The rubidium atoms go into the bright pancakes, and then we change the frequency between these 2 YAG laser beams, and the lattice transfers to the lower chamber where it overlaps the atom. And then we can either study the interaction of the ion with atoms in the lattice, or study the interactions of the ion in a cross laser trap, in a cross dipole trap. And in our group, in the past decade or so, we studied several processes in these mixtures. We studied the non-equilibrium dynamics that results. We studied spin dynamics. We studied excitation exchange processes in which rubidium is being excited, strontium plus is being de-excited from a metastable state, and then rubidium is being excited, and excitation is exchanged between them. We studied the dephasing of an optical clock transition on the ion in the presence of collisions with the ultra-cold atoms. We studied charge exchange. We studied the energy dependence of these mixtures, and we also started implementing quantum logic in these systems to study inaccessible species of ions. And I'm not going to tell you about all these things just due to shortage of time, but what I'll do in the rest of the talk is describe the non-equilibrium dynamics that we get, then spend some time on spin dynamics and its energy dependence, and then end by quantum logic detection of these processes. So I guess this is a good point for you to ask questions if you have any, and if not, I'll move on to describing the different experiments. Okay, so elastic collisions. You know, the naive picture would be, I have an ion. You know, it starts at microkelvin temperatures. I immerse it in a bath of atoms that is also at microkelvin temperatures, and what I expect to get is thermal equilibrium between these 2 guys, and the ion would remain cold. But this is not really the full picture, and the reason it's not the full picture is because the ion is not trapped in a static potential, and the reason for that is that it's impossible to trap an ion in a static electrostatic potential. The reason for that is the Laplace equation. The sum of second-order derivatives in 3 dimensions of the electrostatic potential has to null, and therefore I cannot form a 3-dimensional minimum to the electrostatic potential. And that's why in the pole trap we use a time-varying quadrupole potential. We have a spatially dependent electric field vector And again, I can't play the movie for some reason, which actually annoys me a lot. Maybe I should.
You are sharing the screen, so maybe you could switch to a different program to your file browser and then try to show the movie with Alt Tab or.
Let me do the following thing. I'll stop sharing for a second. I'll move out of presenter mode. I'll re-go into presenter mode. And now I'll reshare my screen. Do you see my screen now?
Yes.
Yes.
Okay. And now the movie would play. Great. So now you see what happens is time dynamics. The electric field vectors are oscillating very quickly, and the ion is being pushed away from the high amplitude electric field oscillations into the low amplitude region. Actually, the trajectory of the ion is a solution of a time periodic Matthew equation. And when you solve this equation, you see that the ion motion can be approximated as the motion of a harmonic oscillator under a static potential, under the approximation that the eigenfrequency of this harmonic potential, omega naught, is much, much smaller than the RF frequency. That the ion, in other words, can't respond to the fast RF frequency, at least not to a large extent. And if you look at the motion of the ion in this secular potential, this is a picture of the trap that we use in our experiments, you see that the motion looks like a harmonic motion, some amplitude times cosine of the harmonic frequency plus some phase. This is this secular motion here, but it has some superimposed micromotion, and that superimposed micromotion is actually proportional. The amplitude of that micromotion is proportional to the displacement of the ion from the center of the trap. The farther it is from the center of the trap, the larger are the RF fields it experiences, and therefore the larger is the amplitude of this very fast oscillation. In many experiments with trapped ions, people really forget about this micromotion if it's small enough. But when we overlap the ion with atoms, we cannot neglect micromotion. Micromotion is actually a very strong factor in these experiments. And when we performed this experiment that was published in 2016, we initialized the ion to the ground state of the trap. The ground state energy was a few tens of microkelvin, 50 microkelvin. We overlapped it with a cloud of atoms, and we have seen that we don't get a Maxwell-Boltzmann equilibrium distribution of the ion at the temperature of the atoms, but rather we see that the ion develops a power law distribution. In this case, it was a Tsallis distribution. This is the formula that you see here. And with a power law that goes down like 1 over the energy square. You see here that the power law, after a few collisions, sort of stopped at a power law that equals n equals 4 here. And with a density of states of energy squared, we got a distribution that scales as 1 over e squared. 1 over e squared is a pretty radical distribution. It doesn't even have an average. Even the average of this distribution diverges. In the last several years, in some theoretical works that preceded our experiment, and some theoretical works that came after our experiment, people have been able to show that indeed, theoretically, this is the case, and this is what you expect. You expect that the energy, this is what you see here is the energy distribution of the ion at steady state. This is not a thermal equilibrium distribution. And actually, you expect to see a power law distribution, and this power law distribution comes from a dynamic that was analyzed by Marko Cetina from Vladan Vuletic group at the time, and he has shown that even if the ion is cool to the ground state of the trap, and even if the experiment works perfectly, you get a power law distribution and you get an energy per collision, which in our case, it's given by this equation here. In our case, it's on the order of 100 microkelvin, and it's the result of a dynamic where the atom pulls the ion away from the trap center, in which the micromotion amplitude is 0, into a region where the micromotion amplitude is non-zero. It actually creates a bound state where the atom and ion collide over and over again at a frequency. The frequency of these very fast collisions is about 100 megahertz. They collide for a few tens of nanoseconds, and then the two depart. But the energy that the ion receives is about 100 microkelvin. Again, remember that in order to get to the S-wave regime, we need the ion and the atom to be at about 100 nanokelvin. So 100 microkelvin is 3 orders of magnitude above the energy necessary to go into the quantum regime. So eventually what you get is a parallel distribution. It's a result of a multiplicative random process. I'm not going to go into the details of that, but it's a highly non-equilibrium type physics that you observe here. The next line of experiments I'd like to describe is a line of experiments in which we studied the spin dynamics of an ion which is immersed in a cloud of rubidium. And what we've studied is the spin direction of the ion when we immerse it in a cloud of rubidium atoms that are either polarized. So in the data that you see here, we studied the spin of the ion when it collided with atoms that were polarized in a given spin direction. And what you see is that if you initialize the ion to be parallel to the spin of the atoms, it remains parallel to the spin of the atoms at the 90% level. If we initialize it at a spin direction which is opposite to that of the atoms, you see that collisions align the spin of the ion to be parallel to that of the atoms after 10 collisions or so. Whereas if we immerse the ion in a spin bath that has no preferred direction, in this case, we initialize the rubidium atoms in the m equals 0 direction, you see that the spin of the ion after roughly 10 collisions, 10 Langevin collisions, becomes completely at a mixture of 50% pointing up, 50% pointing down. Out of this data, we could extract the following. It seems like spin exchange, the atom and ion exchange their spin after about 9 Langevin collisions. When the atom and ion exchange their spin, that means that if the ion started spin up and all the atoms started spin down, after 10 collisions, the ion is now in spin up and one atom is at spin down, but that doesn't matter. That atom is probably lost from the track. And now the ion is at spin up, the atoms are also at spin up, and spin exchange can't occur anymore. That's because the spins are parallel. But after 50 or so collisions can occur through which angular momentum is going to go from that combined spin system into the external motion of the atom and ion. In other words, angular momentum is going into motion, and then spin is no longer conserved. And even if you started at spin up case, you're going to find yourself in a spin down situation. That's the reason you're not staying at the 100% polarization, but rather go to 90% polarization. The other thing we realized is that this is an opportunity, and it's an opportunity because if you remember, I told you that charge exchange can only happen in our system if you start on the singlet state, and that is because strontium, neutral strontium and rubidium plus, the ground state is only a singlet. And photons cannot change triplet symmetry to singlet symmetry. So this decay channel from the triplet to the singlet is forbidden. And that's why you must be on the singlet state in order for charge exchange to occur. Now, if we align our ion spin with that of the atoms, that means we're only in the triplet state. And that's why we figured that in the presence of a polarized sample of atoms, charge exchange would be suppressed as compared to a non-polarized sample of atoms. And this is exactly what we've seen in our data. So this is really a way to control, using spin degree of freedom to enable us to control the rate with which atom ion chemistry was happening. Now, when we try to understand why it takes 9 Langevin collisions for spin exchange to occur, we looked into the semi-classical theory of spin exchange occurring, and the semi-classical theory is pretty simple. Really, the cross-section for spin exchange collision is again given now by some overlap integral. So if you like, a matrix element squared connecting our initial state to our output state by spin-spin interaction between the atom and the ion. But then again, similarly to the elastic collision rate, we need to take the 4 pi over k squared factor and then sum the L equals 0 to the maximum angular momentum we have, 2L plus 1, and then sine square. But instead of a single phase that we accumulate over the collision, we need to look at the phase difference between the singlet and the triplet. And the reason is that we can write up down as a superposition of singlet triplet m equals 0, down up as the orthogonal superposition of these two states. And any phase evolution between the singlet and the triplet would render, would evolve up down into down up. So spin exchange is dominated by the phase difference between the singlet and the triplet. And again, in the semi-classical regime, we expect for this sine function to be 1/2. However, our data seem to suggest that we get a sine squared factor which is above 1/2. And to understand it, in theory, and this was a collaboration with a theory group at Reno, Nevada, we have seen that when we actually scan the energy difference between the singlet and the triplet molecular potentials, we can actually vary the cross section for a collision, either in a coupled channel type calculation or in some semi-classical calculation. We have seen that the phase between the singlet and the triplet, while the phase on each one of these molecular potentials, and what you see here is the phase squared, the sine squared of the phase on the singlet purely, on the triplet purely, you see that these two are completely uncorrelated and would average to 1/2. But the phase difference between the singlet and the triplet is actually fixed. And that means that we see an S-wave-like behavior all the way up to 20 partial waves, which is very peculiar. We ended up understanding this effect, and this effect really results from the fact that the singlet triplet phase difference is dominated by short range physics. It's dominated by dynamics that happens over molecular scales, a few Bohr, if you like, maybe a few tens of Bohr, whereas the partial waves have impact where centrifugal forces act, and centrifugal forces act where the centrifugal barriers are, and that's at hundreds of nanometers, very far away from where short-range physics happens. And because of this large separation of scales, the phase difference between the singlet and triplet really does not depend on which partial wave you are, all the way really to millikelvin. And this is really an interesting physics to try and observe. And this is what we're working on now, and I'll share that towards the end of the talk. And this is also why, as you scan the energy of the collision, theory predicts that you should be able to see these shape resonances happening, even when you have 20 partial waves involved. And this is, the last part of the talk. I'll describe experiments in which we scan the energy of the collision in search for these shape resonances. So an experiment like ours, how can we change the energy of the collision? It's actually fairly simple. What we do, and I described before how we shuttle the atoms from the upper chamber to the lower chamber. We load these atoms into a one-dimensional optical lattice, and then by scanning the frequency difference between the two lattice beams, we shuttle the atomic cloud down to the ion, and then we can actually by controlling the frequency difference between the two beams, we can control very precisely the velocity with which these atoms are moving across the ions in the lab frame. So by doing so, we can control the collision energy of the atoms across the ions. Our resolution is about 100 microkelvin. If you remember, that's the energy which is given inherently to the ion in a single collision. This is roughly also the level to which we can compensate our micromotion. That's the, if you like, the technical limitation to our resolution. And we can scan this way the energy of the collision between 200 microkelvin all the way to about 12 millikelvin in a very precise way. one thing we need to make sure of is that per pass, we have only a single collision, and that is because a single collision happening at 12 millikelvin would already largely heat up the trapped ion, and therefore subsequent collisions would not be cold anymore. So we control the density of the cloud such that the average probability per collision is on the 10-20% level, and therefore the probability of a second collision given a first collision is of that order. One nice thing to notice about this technique is that the probability for collision goes like the collision rate times the collision time. Now, because the collision rate is given by 1 over the velocity, and the collision time is linear in the velocity, you actually get, the collision rate is proportional to the velocity, and the collision time goes like 1 over the velocity term falls out. And that's why you get a collision probability which is directly proportional to the cross-section of the collision. So the collision probability here should recover, for example, in the semi-classical regime, the Langevin 1 over square root E collision cross-section immediately. And that's actually a very nice feature in this experiment. So what you see here is unpublished preliminary data in which we scanned the collision energy and looked for the spin exchange cross-section as a function of the collision energy. The numbers here are pretty small. Do you see the X and Y axis in these figures?
Yes, we do.
Yeah.
You do? Okay, good. Good. So, to begin with, we work at a finite magnetic field, and we have to work at a finite magnetic field. Otherwise, it's very difficult to control the ion different energy levels. And at this finite magnetic field, the energy gap between up, down, and down, up. The reason the up, down, and down, up, and one spin state is the atom, one spin state is that of the ion, they're non-degenerate. And the reason they're non-degenerate is because the rubidium atom has has nuclear spin. The strontium ion does not. Anyway, there is an energy gap between up, down, and down, up. And at 3 Gauss, it's 1.5 millikelvin. And that's why we thought, okay, we want to study spin exchange as a function of energy. We need to study the exothermal direction of the spin exchange rate. So, it wouldn't cost us energy to flip this, to exchange the spin between the ion and the atom. And this is the blue data that you see here. And indeed, when we plot this cross-section as a function of energy up to 3 millikelvin, you see that this, the black line here is a fit to the data, and the fit gives us a power law, which is to a very good, within our experimental precision, is 1/2. So we recover the Langevin cross-section prediction. We see some deviations, but these deviations are consistent with statistical noise. In other words, we don't see, as of yet, shape resonances or quantum signatures in these collision rates. In order to make sure that we're sufficiently cold, we said, okay, let's measure the endothermic part of the reaction. If we measure the endothermic part of the reaction, we expect to see 0 reaction when we work at temperatures of about 100 microkelvin or 200 microkelvin, 0.1 millikelvin. And that is because we need to pay a toll of 1.5 millikelvin, 15-fold larger energy. We're not going to see any reaction rate. We're only going to see the reaction rate, emerging when the energy is sufficiently high in the collision. But instead, what we see is, we see that indeed, when the collision energy is 3 millikelvin, which means that in the center of mass frame, not in the lab frame, the collision energy is 1.5 millikelvin. I remind you that the mass of rubidium and strontium is the same. Indeed, the endo and exothermal reaction rates converge. They're the same. But we see roughly half the rate at 0.1 millikelvin. And that drove us nuts. How come we can pay in a single collision, I remind you, we can pay as much energy and flip the spin of the ion? And the only explanation we could come up with is that the atom and ion form a bound state that lives sufficiently long, not for a single collision to occur, but for many, many, many collisions to occur. And these many, many collisions, and as we have seen before in this non-thermal equilibrium scenario, can pump energy into the system due to the non-stationary RF fields in the trap. And when we simulated this, actually, one other thing we did is we performed thermometry on the ion following both an exothermic and an endothermic collision. And we saw that it doesn't matter, even if we did an endothermic collision and we had to pay 1.5 millikelvin, we found an ion that is much hotter. It's roughly 1 millikelvin hot, much, much hotter than the ion we started with, which really, increased our confidence that, energy is being pumped over a long time. And actually in simulations that we run, these are classical simulations, we see, a hint that this is indeed the case. What you see here is the ion trajectory. That's that oscillating blue curve here, the approaching atom. You see that in pink or pink data, you see the distance between them go to 0. You see that similar to the Satina model, they form a bound state. But in this case, this bound state actually lives for quite long. The reason the bound state happens is because of an endothermic spin collision. You had to pay energy in order to flip the spin, and that's why you now ended up in a bound state. And you see that this bound state actually lives for 2-3 microseconds, which is a really long time for this quasi-bound molecule. You also see that the oscillation frequency of the ion in the trap changes by a factor of √2, which is an indication of now twice as heavy molecule oscillating in the pole trap. And if we zoom in even further, we see that during this collision, we get hundreds and hundreds and hundreds of collisions. Some of these collisions actually flip the spin of the ion and the atom back and forth. That's why you see these collisions as cold and then hot and then cold and then hot. But even if the spin is flipped, it's not enough energy to be released from this bound state until eventually the RF pumps more and more energy into the system and the atom and ion move away. So we believe that the fact that we see endothermic spin reaction rates not going to 0 is an indirect indication of the formation of these relatively long-lived molecular states. And that's something that we're in the process of studying both in simulation as well as in the laboratory. I see that I only have about 2 minutes or so, and in the 2 minutes that I have, I would like to actually speak about the title of my talk, and that is how we're using quantum logic techniques in order to study these atom-ion spin collisions. So all the experiments I've shown you so far, in fact, all the experiments you'll see in this field, almost to 100%, really benefit from the fact that, as I mentioned at the onset, these trapped ions are probably the best platform to perform coherent control. We can prepare their spin, we can laser cool them, we can read out their spin, we can prepare superpositions, we can really do anything we like with these trapped ions. That's why they're such a good platform for universal quantum computing. But when we want to study chemical reactions and the interaction between neutral atoms and these trapped ions, sometimes we want to use ions that are not controlled so well. Maybe we want to use molecular ions, or we want to use highly charged ions, or we simply want to use atomic ions that we don't have the laser wavelengths to investigate. How can we do that? And that reminds of a very similar problem people have looked into about a decade, or solved with a very elegant technique about a decade ago, and that is the problem of spectroscopy. We can perform very precise spectroscopy on trapped ions, but we don't have very good tools to investigate spectroscopically every ion we would like. Some ions we can't access. And an idea by Dave Wineland from 15 years ago, Dave Wineland said, fine, that's not a problem. Let's put in a 2-ion crystal an ion that we can control very well together with the ion we can't control and we would like to investigate. So the blue ion here is the spectroscopy ion. The red ion is a logic ion. We can probe the spectroscopy ion and then map the state of that spectroscopy ion to the probe ion. And after we map the ion from the spectroscopy ion to the logic ion, we can read out this spectroscopy ion. This really brilliant idea led to the development of for example, I think the first demonstration was the aluminum plus ion quantum logic clock. This is among the 3 most precise clocks to date. And in 2008, 2010, that was the most precise clock on Earth. People since, both at NIST and then by Pete Schmidt at PTB. Pete Schmidt was also one of the pioneering authors on this experiment. Use this technique in order to perform spectroscopy over molecules, and this is now a more wider and wider spread technique. Again, at PTB, the group of Pete Schmidt has used this in order to perform spectroscopy on highly charged ions, ions that were charged by 17 electrons or so. So this is really a powerful technique. So the idea we followed was the following. Let's do exactly the same thing in order to study chemical reactions. We'll prepare a 2-ion crystal in our lab. In one of the ions would be the logic ion, the ion we can control perfectly. The second ion would be the chemistry ion, an ion that we can't control, but that's the ion we would like to investigate the chemistry of that ion with a neutral atom sample. We'll then overlap the 2 ions with the cold atomic cloud. And in chemical reactions that are exothermic, energy would be released into this ion pair. But now it's very easy for us to investigate this energy release. We do that by investigating the logic ion. So the logic ion would be heated through sympathetic heating, and we can actually tell whether the logic ion has heated up or not very easily, for example, by performing temperature-dependent fluorescence. And we detect fluorescence if the ion is hot. We don't detect fluorescence if the ion is cold. And so we implemented this idea. We start from a 2-ion crystal. In this case, you can see a strontium-88 ion, which is the ion we control very well, together with a strontium-86 ion that we can't control simply because we don't have the correct laser wavelengths. We then let this 2-ion crystal interact with a cold cloud of rubidium, and then by investigating the heating up of this strontium-86 ion, we can tell whether an exothermic reaction happened or not. So we did this experiment. The reaction that we investigated was spin exchange, but the type of spin exchange that releases hyperfine energy. So we initialized rubidium atoms in the F=2 excited upper hyperfine state. Some part of spin exchange reactions release that hyperfine energy, and then we can measure that 330 millikelvin energy that is released into that 2-ion pair and detect the reaction rate. We started off by calibrating this experiment on 2 strontium-88 ions that we can measure very well. We did this by preparing both strontium-88 ions in the down state. I apologize, there should have been here 2 ions pointing down and 2 ions pointing up. And we do that, repeat that experiment by preparing the rubidium atoms in all possible spin states in the F=2 manifold. We see that when the atomic spin is anti-parallel to the ion spin, the reaction rate is high. It's dominated by spin exchange. When the 2 spins are parallel, we see that the reaction rate is small. That is because the only way to release hyperfine energy is through spin relaxation that couples angular momentum into the orbital momentum, the external degrees of freedom of the atom and ion system. And we see that these 2, if we start the ions in down state and in the up state, we expect to see a mirror image of this data. And indeed, we see that mirror image to a very good approximation. Now we switch to a situation where we have 1 strontium-88 ion and 1 other isotope of strontium. We worked with strontium-86, 84, and 87. And by comparing the rates that we measure here to the calibration experiment here, we can actually extract the spin exchange reaction rate of strontium-88, strontium-86, strontium-84, and strontium-87. And we actually think that we see, the quantum, away from S-wave quantum signature that I told you about before. But in order to be convinced, we actually have to compare that to a theoretical calculation, which Michal has kindly agreed to work with us on, and hopefully we'll be able to nail that down. And I'll end by showing you a different set of data using this quantum logic technique in which instead of having two different isotopes of strontium, we have a strontium ion and a rubidium plus ion. And here we're measuring resonant charge exchange reactions with rubidium plus. Again, these reactions have to lead to hyperfine energy release. And we measure that hyperfine energy release to be significantly smaller than the Langevin rate that you see here, which we believe, again, is a very strong indication of a quantum signature of the collision reaction rate and a strong deviation from the Langevin cross-section. So I think well, I hope I convinced you that atom-ion interactions are an exciting topic. And I think that both in our group as well as in other groups, we're now starting to open the window into the quantum regime of atom-ion interactions. And with that, I will end. I'll just say that I'd like to thank my group members. This is a recent picture taken from a trip of our group to the Dead Sea. That's why we're also dressed a little bit biblically. I should mention also that we're not just working on ultra-cold atom-ion mixtures in our group. We're also working on quantum computing and simulations, metrology and atomic clocks, precision measurements, and searches for physics beyond standard model, and also on neutral atom and mixtures of Bose-Fermi ultra-cold quantum degenerate gases. And I'll end by saying that we're the very pretty Weizmann Institute of Science, and we have available postdoc positions if this is your next step in your career. And I'll thank you for your attention and open the floor for questions.
Yes, thank you very much. Now, if you have some question, please just ask them. Unmute you.